Hey friends, welcome to the YouTube channel All About Electronics. In the previous video, we briefly understood about the 555 timer IC and we had seen the pin diagram as well as the internal block diagram of this 555 timer IC. So in this video, let us understand how we can design a monostable multi-vibrator using this 555 timer IC. Now in the earlier videos, we had seen that this monostable multi-vibrator has only one stable state. So the output of this monostable multi-vibrator used to be in a stable state, but whenever a trigger signal is applied, then momentarily the output of this monostable multi-vibrator goes into the unstable state. And after a certain time, it used to come back into the stable state. So whenever this monostable multi-vibrator is designed using the 555 timer IC, then it can be used in many applications. For example, it can be used for generating a timing delays which can be used for turning on the relay for certain time. Apart from that, it can be used for the frequency division as well as for the pulse width modulation. So now let us see how we can design this monostable multi-vibrator using the 555 timer IC. So here is the circuit diagram using which we can design a monostable multi-vibrator using this timer IC. So as you can see over here, the discharge and the threshold pins are connected together, and using the resistor R1, they are connected to the supply voltage, while using the capacitor C1, they are connected to the ground terminal. So over here, this reset pin is connected to the supply voltage, and here the trigger signal is applied at pin number 2. And over here, as we are not using any external control voltage, so this pin number 5 is connected to the ground through this capacitor. So now to understand the working of this circuit, let us draw this circuit along with the internal block diagram. So here the same circuit is drawn along with the internal block diagram. Now here, to understand the working of this circuit, initially let us assume that the output of this 555 timer is equal to 0. So whenever output is 0, at that time this Q bar will become 1. And whenever Q bar is equal to 1, at that time this transistor will become on. And the output of this pin number 6 and 7 is connected to the ground through this transistor. So whenever the output of this 555 timer is 1, at that time this capacitor C1 will remain at a ground potential. So we can say that whenever the output is 1, the input to this first comparator is equal to logic 0. Now like we had seen in the previous video, the voltages at these two nodes will be equal to 2/3 VCC and 1/3 VCC respectively. So whenever this pin number 6 is at ground potential, then the first comparator output will be equal to logic 0. Because the voltage at this inverting node is more than the voltage at this non-inverting node. On the other end, if you look at the second comparator, whenever the trigger signal is not applied, at that time this pin number 2 is at VCC voltage. So at that time the voltage at this inverting node is more than the voltage at this non-inverting node. So at that time the output of the second comparator will be also equal to logic 0. So in that condition both R and S are 0. So the output of this flip-flop will remain in the previous condition, and in this condition the output of the 555 timer will remain 0. Now let us see what happens whenever we apply the trigger signal. Now here the trigger signal is applied in such a way that during the triggering action the output at this pin number 2 goes below this reference voltage. So whenever the triggering action happens, at that time the voltage at this pin number 2 goes below this reference voltage. So at that time the output of the second comparator will become logic 1. Now during this triggering action, as this Q bar is in logic 1 state, so this pin number 6 will remain at a ground potential. So the output of the first comparator will remain at logic 0. So during the triggering action, if you see, S is equal to 1 and R is equal to 0. It means that we can say that this flip-flop will get set to the logic 1. And whenever this flip-flop output is logic 1, at that time the output of the 555 timer will also get set to the logic high. So now whenever this Q will become 1, this Q bar will become 0. And as soon as this Q bar will become 0, this transistor will get switch off. And now this capacitor C1 will start charging through this path. So once this triggering action happens, this capacitor C1 starts charging towards the supply voltage. Now after this triggering action happens, the voltage at this pin number 2 is equal to supply voltage. So once again, the output of the second comparator will become logic 0. Now during the charging process of this capacitor, whenever the voltage at this pin number 6 just crosses this 2/3 VCC voltage, then the output of the first comparator will become logic 1, because at that time the voltage at this pin number 6 is more than the reference voltage. So in that condition, now if you see here, this R is equal to 1 and S is equal to 0. So at that time the output of this flip-flop will become logic 0, and in a way we can say that at that time the output of the 555 timer will become logic 0. So in this way, momentarily the output of this 555 timer goes into the unstable state, and then after, whenever this capacitor voltage just reaches this 2/3 VCC voltage, then the output will come back into the stable state. Now as soon as this Q will become 0, this Q bar will become 1, and whenever this Q bar is 1, then this transistor will get again switched on, and the voltage across this capacitor will get discharged through this path. And once that happens, both output of the comparators will become logic 0. So if we see this sequence in a timing diagram, then it will look like this. So whenever this triggering action happens, that means whenever the voltage at the pin number 2 just go below this 1/3 VCC voltage, then the output of the 555 timer will go to the logic high value. And at that time the capacitor will start charging towards the VCC voltage, and as soon as the voltage across this capacitor just crosses this 2/3 VCC voltage, then the output of the 555 timer will become logic 0, and immediately the capacitor will get discharged through the transistor. So in this way, after the triggering action for a certain time period, we will get the output pulse. So over here, the duration of this pulse will depend upon the charging of this capacitor. So in a way, it depends upon the value of R, C as well as this threshold voltage. Now here we are assuming that we are using the internal reference voltage, and in that case the time duration of the pulse can be given by this expression, that is 1.1 times R1 into C1, where R1 and C1 are the external resistors which is connected between this pin number 7 and 6. So in this way, using this resistor and the capacitor, we can design a monostable multivibrator and we can change the timing of this pulse. Now like I said, this monostable multivibrator is useful in many applications. The first one is for generating the different timing delays. So like I said, by changing the value of this R1 and C1, we can generate a different time delays. So if we use the internal reference voltage, in that case, this time will be equal to 1.1 times R1 into C1. Now let us say we want to generate a time delay of 1 second. That means the duration of this pulse width should be equal to 1 second. So for that, let us assume that C1 is equal to 10 microfarad, and correspondingly let us find out the value of this R1. So here T is equal to 1 second, and if we put all these values in this expression, then the value of R1 will be roughly around 91 kilo ohm. So using these values, we can generate a time delay of 1 second. So this is the one of the application in which this monostable multivibrator can be used. Apart from that, it can also be used for the frequency division. Now here at this pin number 2, suppose if we apply a periodic triggering signal, then it is possible to use this monostable multivibrator for the frequency division. But over here we need to ensure that the time duration of the output pulse should be slightly more than the time period of this triggering signal. That means this t should be greater than this time period. So in that case, the output signal frequency will be half than the trigger signal frequency. Apart from that, this monostable multivibrator can be used for the pulse width modulation. Now, so far in our discussion, we have only used the internal reference voltage. But suppose if we use this control pin and if we apply a modulating signal at this control pin, then it is possible to generate the pulse width modulated output. Because in that case, the reference voltage will continuously change based on this modulating signal. And depending upon that, the output pulse width will continuously change. So in this way, we can also generate the PWM output. Now, so far in our discussion, we have used this expression for calculating the pulse duration. But now let us also see how we have arrived to this expression. So this expression can be found by finding the charging time of the capacitor. And if you are aware, the charging voltage of the capacitor can be given by this expression, where here V0 is nothing but the supply voltage. And the same expression can also be found from the expression that we have used during the transient analysis. That is, the voltage across the capacitor will be equal to the final voltage plus V initial minus V final times e to the power minus t by RC, where this final voltage is the voltage towards which the capacitor is charging. So in this case, it will be equal to VCC voltage, while the initial voltage across the capacitor is 0. So if we simplify this expression, then we will get the same expression, that is Vc of t will be equal to VCC times 1 minus e to the power minus t by RC. And over here, we want to find the time t1 where the output of the capacitor reaches this 2 by 3 VCC voltage. So at that time, the output of the capacitor will be equal to 2 by 3 VCC voltage. And this expression can be written as VCC times 1 minus e to the power minus t1 divided by RC. So if we simplify this expression, then we can write it as 1 by 3 will be equal to e to the power of minus t1 divided by RC. And if we take the natural log on both sides, then we can write it as natural log of 1 by 3 will be equal to minus t1 divided by RC. Or we can say that t1 will be equal to RC times natural log of 3. And this value will be approximately equal to 1.1 times RC. Now over here, as we have used resistor R1 and C1, so this expression will become 1.1 times R1 times C1. So using this expression, we can calculate the time for which the output of this monostable will go into the unstable state. Or in a way, we can say that using this expression, we can calculate the value of the time delay. So I hope in this video you understood how we can design a monostable multivibrator using this 555 timer IC and how it can be used for the different applications. So if you have any question or suggestion, do let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.